Once you define variables, a data analysis process can usually be described as a series of functions applied to the data. R includes several predefined functions. We've already shown the install.packages, library, and ls functions. We've also shown you the sqrt function, which computes the square root. We use that to solve the quadratic equation. Now there are many more functions, and even more can be added through packages. Here we review some important information related to functions, and we show you how to learn about functions and tell you a little bit about what's available. Note that these functions do not appear in the workspace, but they are available for use. In general, to evaluate a function, we need to use parentheses. Note, for example, that if you don't, let's say we type the function ls without using parentheses, what it does is it shows us the code for ls. It doesn't evaluate the function. Here you can see the code if you just type ls into your console. Now, if I add the parentheses, so if I type ls, open parentheses, close parentheses, now the function is evaluate, and you see the objects in the workspace. Unlike ls, which doesn't require any arguments, most functions require at least one. Here's an example of how we assign an object to the argument for the function log, a very simple mathematical function that computes the natural log. So if I type log of 8, that's the argument, 8 is the argument, I get in return the log of 8, 2.079442. Now remember, a is an object that we've defined before. We defined this in a previous video. Let's define it as 1. So we can apply a function to a variable as well. Instead of a number like we just did, we can type log of a. Because a has been defined as 1, then the log of a here is 0. In R, functions can be what we call nested. What we mean by nested is that you can call a function to get the argument that's going to be used by another function. Let's give you an example of this. If we type the function exp, x stands for exponential, we get e, the mathematical constant e, to the 1, 2.718282, ... If we compute the log of that number, we should get back 1. These are inverse functions. So note that if we type log, the function log, and then we inside that function, we use the argument function exp, again parentheses, and put a 1, we first evaluate the first function, x1, and then we evaluate the second. And we get the answer of 1, again, because these are inverse functions. So the important thing to remember is that functions are evaluated from the inside out when you nest them. Another very important thing to know about functions. You can learn about them by using the help system. A very nice feature of R is that it documents its functions and that we can call help files and get much information about them. Help files are like user manuals for the functions. You can find out what the function expects and what it does by reviewing the very useful manuals included in R. You get help by using the help function like this. Help, open parentheses, and then the function name in quotes. For example, here's the help for log. For most functions, you can use a shorthand, which is the question mark followed by the function name, and that will show you the same help file. The help file will show you what the function is expecting. These are the arguments. We call these the arguments. For example, log expects an x, a value, and it also expects space. You can see that from looking at the help file for log. However, some arguments are required and others are optional. You can determine which arguments are optional by noting in the help document that a default value is assigned with the equal sign. For example, the base of the function log defaults to the base of x to the 1. It's the natural log. If you already know how the function works but need a quick reminder of the arguments, you can use the args function. If I type args of log, it shows us the 2 arguments that it needs. You can change the default value by simply assigning another value. For example, if we instead of natural log we want to get log base 2, we would type, for example, log of 8, and now we change the default of base to 2. I get the answer 3. Note that to specify arguments, we use the equal sign. We did not use the assignment argument. If we read the help file for log, we see that the first argument has a name too. It's x. However, we haven't been using that argument name. We could though. Here's how we would do it. We would type log x equals 8 and then base equals 2. We get the same answer as if we hadn't used the name x. The above code works, but we can save ourselves some time because if no argument name is used, R assumes you're entering arguments in the order shown in the help file or by args. So by not using the names, R assumes that the arguments are x and then the next one is base. We said that functions need parentheses to be evaluated, but there are some exceptions. Among these, the most commonly used are the arithmetic and relational operators. For example, 2 to the 3, that function that takes 2 to the power 3 doesn't need a parenthesis. We just write it out as we would do in a mathematical formula. You can see the arithmetic operators by looking at the help file for example, the plus operator. So we would type help and then in quotes plus. That'll show us all the mathematical operators. We can also get help with a question mark, but we need to include quotes for these particular operators. Functions are not the only pre-built objects in R. There are also data sets that are included for users to practice and test out functions. You can see all the available data sets by typing data, parentheses, parentheses. This shows you the object name for these data sets. And these data sets are objects that you can use by simply typing the name. For example, if you type CO2, one of the pre-built data objects, you will see CO2 measurements from a particular measurement station. There are also other mathematical objects that are also pre-built, such as the constant for pi and the infinity number. You can see them by typing pi or typing inf. Now, when we are writing code, you want to think about the names you use for your variables. You want your code to be readable. In the examples we've used up to now, we have used very simple variable names. We have used the letters A, B, and C. But variable names can be almost anything. You want to choose variable names that make your code readable. You want to choose variable names that will later be clear to you what you meant to do in your code. Now, there are some rules in R. Some basic rules are that they have to start with a letter and they can't contain spaces. You also want to avoid using variable names of objects that are already defined in R, because that will cause a lot of confusion. For example, don't define a variable and call it install.packages, because that's already a function in R. A nice convention to follow is to use meaningful words that describe what is stored, stick to lowercase, and instead of spaces, use underscores. So for example, for the two solutions in the quadratic formula, we can use the name solution underscore 1 and solution underscore 2. When we write our code, we're going to be writing them into scripts. So for example, if we wanted to solve another quadratic equation, 3x squared plus 2x minus 1, we could just simply redefine a, b, and c and use the same code that we wrote before. So we would change the existing script, which had a, b, and c as 1, 1, and minus 1, and just change those three numbers. If we save the script, we wouldn't have to rewrite everything. We simply change those three numbers. By creating and saving a script, like the code above, we would not need to retype everything and just, again, simply change the variables. So try writing a script into your editor and see how much easier it is to execute code when you've already saved the script. Finally, another way you can make your code more readable is by including comments. If a line of our code starts with the hashtag or with the number symbol, it is not evaluated. We can use this to write reminders of why we wrote the code we wrote. For example, in the script that we just wrote for the quadratic equation, we can include simple comments like these. When we read it in the future, we'll be reminded of why we wrote these particular lines of code.